All right, in 2.7, we're looking at the precise definition of limits. So I'd like to go over that a little bit, and then we'll do an example. When we have this expression, this statement here, the limit as x goes to a of f of x equals L, we talked about that, meaning that we can make the function f of x as close as we like to the limit L. And we can do this by taking x, the input values, sufficiently close to this value a. Now, when we say f of x as close as we want, we mean really as close as we want for any value. And but that's not really a rigorous definition, as close as we want, or x sufficiently close. We'd like to make those a bit more precise, and here's some, I guess, a more precise way of talking about a limit. So when we said we wanted f of x to be as close as we like to L, we make that more rigorous by saying for all epsilon greater than 0. And this epsilon then represents the as close as we want to L. If we look at the picture here, we have a function, this blue line, this blue curve, and we have this limit situation going on. And here we have the limit L, and when this epsilon is some tolerance around L. And we can see that here by these solid red lines. Now, how do we get this curve to be within this tolerance of L? Well, we do that by picking a delta, such that when x is within delta units of a, we get the behavior that we want, that f of x minus the limit, as in the distance between the function and the limit, is less than epsilon. Right? So let's go to the graph here. If this is our particular tolerance, epsilon, let's say, then we can visualize the delta, right? That is the tolerance around the input that would allow the output to be between or to be within epsilon units of L. And we can see that by the intersection of the curve here with this tolerance line. So L minus epsilon, here's the curve. So we can draw a vertical line from that point of intersection down here. And also, so here's the upper line here, intersects right about there. We'll draw that down. And we'll take the largest interval here. That's going to be the delta. So this could be A plus delta. And here, somewhere over here, would be A minus delta. This isn't a symmetric interval because of the way the function curves here, but we take the largest one. And then as long as, we need to take the smallest one. So we would take the delta to be this distance right here. All right. So whenever A is within delta units, or whenever x is within delta units of A, right? So let's just pick a value in here like that. It's close enough, right? It's within this interval of A. And we follow it up to the curve right there. Right? We see that the curve is then within epsilon units of L. Now the limit existing, as we've written it here, means that this is true, this situation is true for any epsilon, right? And that kind of characterizes the behavior of the function of making this function as close as we want to L just by choosing x values, input values as close to A. All right. Let's look at a concrete example. We'll have a function, we'll have a value here for x, and we'll have a value here for the limit. Okay, let's look at an example of that. So here we want to prove that the limit as x approaches 2 of this function, 3x minus 5, is 1. All right, and let's just walk through the precise definition of a limit again, and then talk about what we'll need to actually show here. So for all epsilon greater than 0, there exists a delta such that when the distance between x and a, in this case 2, is less than this delta, the function minus the limit, so 3x minus 5, and the limit being 1, is less than the epsilon. All right, so what we need to do is we need to show that for any epsilon we choose, we can find a delta such that this is true. All right, so the first thing we're going to do is start with some arbitrary epsilon. And all we need to do is, well, say that it's greater than 0. So we'll start with that. We're going to let epsilon be greater than 0. Now this is a stand-in for any epsilon that we could choose. We'll go back and pick a couple of maybe an epsilon or so and show how this works for just a single one. But the key point here is that we are going to, by choosing this to be arbitrary, it could be for any. All right. Now, at this point, we need to find a delta that corresponds to this epsilon before we can continue with the argument here. So we're going to do a little aside. I'm just going to put a bar here. And we're going to work out what that delta is. Once we have that delta, we can continue with this, with proving that this limit exists. So if we think about what we need to have here, we need to have this for that particular epsilon. We know f of x and we know L, so we'll write that down. So we've got this function. It's 3x minus 5. We've got the limit, that's 1. And we want that to be less than epsilon. And now we want to find the delta that corresponds to it. Now the delta, right, is going to have this form, x minus the a, and the a here is 2. Right? So we're looking for this x minus 2 less than the delta. And the question is, well, what is, right, the delta? That's the question. Okay, so what we're going to do is manipulate this inequality to make it look like this one, where we have some expression on the other side here that involves epsilon. Maybe x2, but definitely epsilon. All right, so here we can simplify this. So we've got 3x minus 5 minus 1. Negative 5 minus 1 is negative 6. So we've got 3x minus 6 less than epsilon. And if you notice, this 3x and the 6 both have a common factor of 3. We could factor that out. So we have 3 times x minus 2 less than epsilon. And this is a positive 3. We can move it outside the absolute value. So 3 times absolute value of x minus 2 less than epsilon. You can see we're working towards having an expression like this. All we have to do now is divide by 3, and we have it. So absolute value of x minus 2 is less than epsilon over 3. All right, let's go back over this string of inequalities here. We started with the function minus the limit being less than epsilon, and we have simplified it down to where we see what the x value, or how close the x value has to be to 2 to get this to happen. And we see that it's epsilon over 3. That's our delta. So this is our delta. These are equal. All right. Okay, now that we find the delta, we found the delta that corresponds to this epsilon, we can continue with the argument for this limit. So we've let epsilon be greater than 0. We're going to now let delta be equal to what we've determined it needs to be, and that's epsilon over 3. Okay, and now we want to show that when x is within delta of 2, delta units of 2, epsilon over 3 units of 2, then the function is within epsilon units of the limit. All right, so we let delta equal epsilon over 3, and now we're going to show that the function minus the limit is less than epsilon. So we'll start with this, and we're considering that delta is equal to this epsilon over 3. And we know that this is equal to 3x minus 6. You can factor out the 3. We can move the 3 outside, the absolute value. And now we know something about this. Since the delta here is equal to epsilon over 3, x minus 2 is less than epsilon over 3. So we have, this is less than 3 times epsilon over 3. And of course 3 times 1/3 is 1, so this is equal to epsilon. All right, so putting this all together, we have proved that 3x minus 5 minus 1 is less than epsilon, and we did this when the absolute value of x minus 2 is less than epsilon over 3. All right, and this completes the proof. So there's 2 parts to this. The first part would be to start with some arbitrary epsilon and then find a delta that works. Once you've done that, you proceed with the rest of the argument, showing that when you pick this for the delta, as in when we show that, or we assume that x minus 2 is less than the delta here, we get that the function minus the limit is less than epsilon. Right, so 2 parts. Find the delta, then show that that delta works, essentially.